Now I want to discuss a little bit about chaotic diffusion. So I need to discuss about mean motion resonances. And to start with, I speak about the asteroid problem. So now I want to do a different way of reducing my Hamiltonian, which is what Alessandra called the resonant normal form. But I don't use the word normal form because typically normal form means a lot of orders, right? So it's the lowest order normal form possible, essentially. It's a resonant model to me. Essentially now I'm asking the generating function to be such that the new Hamiltonian has the following problem. I will keep again the lowest degree secular terms, so I will kill mean longitudes, but except of a given resonant model defined by the integers k and q. So I assume, for example, I'm in the vicinity of the 1 to 3 resonance or something like that. So I'm keeping these terms in the disturbing function and killing the rest. Although it's not exactly the way to do it. This is the Hamiltonian I had before, and these are the new terms that should go in for a given resonance, satisfying D'Alembert rules, and so on. Again, this is the longitude with respect to Jupiter's pericenter longitude. And the coefficients in front of these cosines are some, to first approximation, constants. They depend also on the eccentricity of the perturber to some power. And you have the gamma, eccentricity squared, to the power of p over 2. Okay? It's an expansion in power series of the square root of gamma, or of the eccentricity, if you like. And according to D'Alembert rules, to leading order, for p here, this is the leading order term, p over 2. This we showed yesterday. Now, in the planar problem, so I have no inclinations, there are q plus 1 such term for every resonance of order q that satisfy the D'Alembert rules. And we call it the resonant multiplet of the k over k plus q resonance. Now, I do exactly the same set of transformations that I did for the secular problem in order to reduce the secular part to this. If I extend the transformation to the whole Hamiltonian, I get something like that. It looks the same, but it's not really, because here, these dp are actually some sums over p. The coefficient is a bit more involved, but formally it's the same. Okay? Now, if I want to say what is this phi, what is the eccentricity that corresponds to this phi, it's what we could call, let's say, resonant free eccentricity or something like that, right? A linear resonant proper element or something like that, but I will just keep it there. Now, I can, in principle, to do that, I should probably first have defined the resonant angle, which is this combination, which has a canonical momentum conjugate to it that is just this one divided by k, and I can substitute here. Then to further simplify, this is, by the way, everything I'm doing is an oversimplification. I just want to make a point at the end. I can expand this to second order in psi around the exact resonant location that the Kepler law gives me. And then I find this Hamiltonian, this j psi is psi minus psi res. Okay, the deviation from the exact resonant value inside the major axis. And this is the Hamiltonian. And this dp that I have here is actually a function of the eccentricity that I showed before. Now, if you would bear with me for a further simplification, let's say that I expand this around a given eccentricity value. So to make this a constant. You make this a constant, essentially what you have is like a pendulum that is being slowly driven by a harmonic oscillator, and this is the nonlinear coupling terms. Okay. And now I want to explore a little bit the structure, and I'm doing the following. Let's say I isolate each term. Having done this a constant, each term is like a pendulum by itself. Okay? What would exact resonant mean? It means that this angle, psi minus p phi minus, should have a frequency which is 0. If I plug this into the equations of motion that come out of the simplified Hamiltonian, I find that the position of the resonance is this. So I find that the different harmonics of the multiplet are spaced with respect to each other by delta j, which is this. Essentially, it's the first approximation of the secular frequency divided by the coefficient beta. So it's a small thing, it's order epsilon. Because this is order epsilon, and this is order 1. So these terms are very closely spaced to each other. Now I can compute also the width of each of these resonances. The width of the separatrix of the pendulum here, which comes out to be the square root of the coefficient in front of the cosine divided again by v. If you don't remember how to do it, it's easy. You find the stable and the unstable fixed point. You plug in the values for the unstable fixed point here, and you compute the energy for the separatrix. But the same energy also should be for this point here, which belongs to the separatrix. So you plug in the value for the angle for the stable fixed point, and you compute the momentum that satisfies the equation. So you compute this delta G. Now there is a very famous criterion, I think it was mentioned also yesterday by some people, Chirikov's criterion, which I will do a sketchy version of. Essentially means that if I have a pendulum here, and at this distance I have another pendulum, I can compute the widths, and I can compute the distance, and I can take the mean value of the width and divide it by the distance. These numbers tell me if the separatrixes are touching or not. Okay? If this number is greater than 1, I expect the two pendula to cross each other, therefore I expect chaotic motion. That's essentially a very simplified version, if you like, of Chirikov's criterion. Now there are different cases which have to do with the coefficients of the resonance. For example, the distance is always of order epsilon. But depending on the value of this, by the way, this is a plot by an old paper by Nesvorin Morbidelli that has been circulated in many transparencies since, but okay. Essentially, if the coefficient is of order 1, then delta J is of order the mass of the perturbing planet square root. Okay? So basically, you have pendula that are almost on top of each other, and the chaotic band is relatively small. Here, the motion is basically close to that which we call a slowly modulated pendulum, in the sense that you would find the angle in integration to librate for some time, then maybe just go on the upper part of the chaotic domain and have some circulations, then come back, and so on. It's very typical. On the other hand, if the coefficients themselves are small, let's say of order mass, then delta J by itself is of order mass, which essentially means jumping from one harmonic of the multiplet to the other in a chaotic fashion. So technically it's a bit different. Now whether it actually means on the long term something different, we will see in a minute. In the first approximation, actually, you can take all the forms, all the sums that I gave you, and write it like that, which gives you exactly a pendulum with a slowly modulated amplitude and phase. And you can do a little bit of an estimate by setting these values fixed with some pre-specified value of the eccentricity and the longitude of pericenter, and compute this pendulum. Then change the values of the slow parameters and compute the pendulum again, and so on and so forth. And for a big enough set of values of the longitude of pericenter and the eccentricity, you can compute the different pendulum. And actually, you can make a short video that I didn't make, would show a separatrix that is expanding and contracting at the rate that gives you the modulation frequency, which is more or less the secular frequency. Okay.
Magnus,
Yes.
The epsilon is the mu.
Yes, sorry, epsilon is the mu, the mass of the planet.
And on the left side, the square root of mu is bigger than mu.
Yes, of course.
So
the size is much bigger compared to the distance.
The size of what?
The size of the separatrix.
But they seem to be. Oh no.
No, I could make it even more. The distance here is epsilon. So you have.
Yes.
No, it's a little bit exaggerated, but the idea is that. Now, in fact, this modulated pendulum approximation, where you freeze the values of the slow variables and you compute the pendulum, and then you freeze at a different level and you recompute and so on, can give you some estimates of the borders of the chaotic domain. Now, to digress a little bit, first order mean motion resonances have a Hamiltonian which is like that. They have only one argument. Okay? And they are spaced. I mean, this is the relation they satisfy Kepler's law, if you like. and their spacing in lambda is given by this relation between integers. And Wisdom was the first to apply actually Tsiganis criteria in this problem, and found out that all first-order resonances up to a certain distance from Jupiter should actually be overlapped. Okay? This is the famous need to the 2/7 law, we call it. This is the result, the end result, and tells you that the region of 1 astronomical unit around the orbit of Jupiter should be empty because all the first-order mean-motion resonance overlap in the Tsiganis space. Actually, it's true, it is empty. We know that in the main asteroid belt, and in fact, it's a general phenomenon because you can do it in an arbitrary system. Let's say here's a planet which is more or less the size of Jupiter and placed at 20 astronomical units from a sun-like star, and these are the widths of the first-order resonances as function of the eccentricity, and you can see that in an integration, almost everything interior to this line disappeared. Okay, after long enough time, everybody escaped. The rest are there. So it really has an application. Now, what I don't have time to discuss, unfortunately, are the big resonances, 2-to-1, 3-to-1, 5-to-2, the Kirkwood gaps. There, the situation is more complicated. The main source of chaos is not the one that I've shown. There, you can have secular resonance inside the mean-motion resonant domain, which would greatly change the orbital elements over millions of years of period, and this is the main mechanism by which the Kirkwood gaps have become Kirkwood gaps. Yeah. Now, you know that there are also three-body mean-motion resonance, meaning that they satisfy such relation for three bodies, let's say asteroid, Jupiter, and Saturn. And because it's a combination of three integers, they are much more dense in the main belt than the single mean-motion resonance, but they are less strong, essentially. You'll see in a minute why. The Hamiltonian you can derive for a three-body mean-motion resonance is very similar to the one you can derive for the two-body mean-motion resonance. It's just harder to derive it, in a sense. Why? Because you start from a Hamiltonian, which is the Keplerian problem, the terms you need to make it autonomous, and the perturbation is actually the sum of two disturbing functions, one for the Jupiter asteroid case and one for the Saturn asteroid. There. Okay? And the two epsilons are the two masses. Now, you can start as before to define, to order epsilon, the average Hamiltonian over all lambdas, which means that to order 1 in the masses, you don't have any resonant combination. You kill everything. However, if you keep track of the second order terms, you will find now cosines which contain linear combinations of the angles of all three bodies as a result of the products that are being introduced by the Poisson brackets there. Okay, so you have product of the cosine of the Jupiter asteroid case times the cosine of the Saturn asteroid case, and this you can cast in the sum of cosines. So essentially, what you find out is that there are in fact two contributions. The direct contribution, which is exactly what I described, the result of the Poisson bracket, and the indirect contribution, because the elements of Jupiter are in fact not constant, they are perturbed by Saturn to order epsilon Saturn. Okay? So if you put in an approximation of the orbits of Jupiter and Saturn because of their interaction, you will find also an indirect term that gives you combinations of the longitudes of the asteroid with Jupiter and Saturn. So these terms contain the three-body mean-motion resonance, whose size is proportional to epsilon square, actually to the product of the masses. Okay? So they are formally much smaller in size, but I can tell you that the low-order three-body mean-motion resonance are probably as important, if not more, than the high-order simple mean-motion resonances with Jupiter. And there are several works on that. Now, if I take the simplified sketch that I did before, so you take each term, this is from Nesvon and Morbidelli. This is the 5 minus 2 minus 2 three-body resonance at 3.17 EU, and this is the 3 minus 1 minus 1 I get at 275 EU. So you take each harmonic of the multiplets separately, and you plot the weight of the separatrix, you have such a picture. So of course it does not tell you much about the real dynamics. What it tells you is that this resonance, which is 0 degree in eccentricity, this resonance, which is first degree in eccentricity, that's why it's straight lines, and this resonance with second degree in eccentricity, so on, are actually overlapping to a great extent because their distances are much smaller compared to the widths. Okay. Now, there is an important and strange, in my opinion, result in the following sense, that indeed, low-order three-body mean-motion resonances and high-order simple mean-motion resonances give more or less the same diffusion timescale. The reason it has to do exactly with the coefficients that I showed before. The width of the three-body mean-motion resonance is proportional to mass squared, but the d coefficient is of order unit. Okay, so the delta j is of order epsilon. Delta j squared over the appropriate timescale is a measure of the diffusion. So epsilon squared divided by 1 over epsilon gives you epsilon to the power of 3. For a high-order simple mean-motion resonance, it is proportional to square root of the mass of Jupiter times the coefficients, which is small, let's say of order epsilon. Therefore, delta j is of order epsilon, delta j squared over a timescale is a gain of the order of epsilon cubed. And since epsilon is, let's say, the mass of Jupiter, 10 to minus 3, what you get is a timescale of the order of 1 billion years, let's say. And it's actually true in numerical computation that if you take out the main mean-motion resonance and you work inside the main belt, trying to find numerically this long-term diffusion, you see that basically the timescale for an orbit to, let's say, escape or reach high enough eccentricity to enter the Mars crossing region is of order 1 billion years throughout the belt. Now, I will finish with an example, essentially. It will take some time, but that will be the last thing I will speak about on asteroids, which is the example of the asteroid Veritas, in the family of Veritas. Now, before a few years, I knew that if I would look for Veritas, I should look in Vino, as everybody here knows. That's the official guideline, right? However, it so happened that we met with Zoran and we started working together, and then we decided to spend a little bit of effort on this problem. Now, the family of Veritas is this small cluster here of asteroids at 3.17 something astronomical units. And it's interesting because although it appears a small niche, it's actually cut through by several resonances of mean motion, either two-body or three-body, the most important, if you like, of which are the 5 minus 2 minus 2 resonance and the 3 3 minus 2. Now there is, of course, a very long history of the problem, starting with original simulations by Milani and Farinella, correct?
20 years ago.
Yes, showing that the Veritas itself could escape from the family within 50 million years or so, if I remember the number. Then there was the question of which resonance is most important and so on. Several people worked on that as well. And eventually, we worked also with Zoran because we wanted to understand the intricate shape of the family and really how it got as dispersed as it looks. So, cut a long story short. You start by taking all the bodies that we knew at the time and compute the orbits and compute what Andrea talked about before, the Lyapunov time. I don't know if everybody's familiar with terminology, but basically, as you know, chaotic orbits diverge exponentially in phase space, and the mean exponential rate is what we call roughly the maximum Lyapunov exponent, and the inverse of that is a time scale. The shorter the time scale, the more chaotic locally the orbit is. Okay? So this is a plot of a few hundreds of test particles, this is the gray line, around the region of Veritas, showing that basically a large fraction of the phase space is chaotic there, and the dark dots are the real bodies of the family. And you see that they are really placed on the borders and on the along the center of the main resonances. This is the 5 minus 2 minus 2, and this is the 3 3 minus 2. So most of them are chaotic. But they do have a little bit different evolution. Let's say, start with the short-term evolution. This is an asteroid that is next to Veritas in the 5 minus 2 minus 2 mean motion resonance. And this is the angle 5 lambda asteroid minus 2 lambda Jupiter minus 2 lambda Saturn plus minus the perihelion of the asteroid in order to satisfy the D'Alembert rule. And what you see is that the variation of the semi-major axis correlates very well to the variation of the angle, which for the most part is actually doing librations, as you can see. So it actually, the semi-major axis oscillates at this time scale around the center of the resonance, but for some time it may be that it goes up in the uppermost borders of the chaotic domain, so it does a few circulations, and the semi-major axis oscillates with smaller amplitude above the center of the resonance, near the border of the separator, and so on. Now, if I take an asteroid in the other mean motion resonance, the 3 minus 2, it has a different type of evolution. You see that basically the mean value essentially takes small jumps, and the rest of the oscillation is unimportant. The eccentricity is almost not affected by it. And you have different angles, different combinations satisfying the D'Alembert rule for the same resonant ratio, so different harmonics of the same multiplet, that may show the typical chaotic behavior of transition from libration to circulation, and some others do not, meaning that not all harmonics overlap, at least to the same extent, for this eccentricity. Okay, so this is the two different types of chaotic motion that I showed in the sketch. Now, if you look at the proper elements of the real bodies, which are the triangles here, this is the distribution. This is the part of the family that's in the 5 minus 2 minus 2, and this is the part of the family that's in the other resonance, and the rest are largely regular. And if I take each of these and I integrate and I compute analytical, I think it was Zoran who did the computation, proper elements time series, you will see that these bodies diffuse all over the resonance on a 100 million year time scale, while these ones do not diffuse all over the resonance. They are restricted in smaller areas along the resonance because not all harmonics overlap. In fact, this characteristic mean line is very reminiscent of the line that I showed in the sketch yesterday, along which a particle moves in the single resonance approximation, which is a function of semi-major axis and eccentricity that has to be conserved roughly. Okay, so there is chaos, but it is restricted within thinner layers in proper element space. In fact, you can measure the diffusion rate. So you take a bunch of orbits, either the real objects or fictitious objects that you assume were roughly here when the family was created, and you let them diffuse in the numerical simulation, and you measure the mean diffusion rate for a few million years. This is the curve. This is the mean square displacement in the eccentricity-related momentum as a function of time, and it's roughly linear, which could be. So it's a good approximation of a real diffusion process, and the slope of the curve is the diffusion coefficient in this value. Okay? So this group really diffuses with some value. If I do the same curve for the other group, I find something which is 2 to 3 orders of magnitude less. So you have two different types of chaotic motion, one which is clearly diffusing and one which is not, essentially. Now, this tells me that I cannot use this part of the family to do a meaningful estimate of the age of the family. Okay, but I can use that part, and in fact we constructed a simple one-dimensional diffusion equation using these numbers, and we did a Monte Carlo simulation to see when the current extent of the family will be reached if we start from a much smaller initial configuration, and the statistics say 8.7 plus or minus 1 point something million years, which is a number that you can take like that. But the good thing is that it's also almost the same number that you would get if you estimate the age of the family from the regular component. And the way to do it is you take these orbits, which are regular, and they are a little bit dispersed in semi-major axis. So if they were created in a point, because they were dispersed, they have slightly different secular frequencies. So after 10 million years, you would not really recognize immediately that they are the same members of the family in oscillating space. Okay? Now, if you take this and you integrate backwards in time, you will find that their nodes cluster at 8.3 million years in the past. So both the regular component of the family and the chaotic component of the family give you roughly the same estimate for the age of the family. Okay? This is very nice, but it is clear, I guess, from this example of a tiny family in the main belt that not all resonances lead to large-scale diffusion in proper element space within at least a minimum time. And I'm very tempted to say that these bunch of guys are very reminiscent of the behavior that was described by Milani Nobili as stable chaos, kind of an oxymoron, on which I worked during my first year as a researcher, but to my regret, I cannot say I really understand it up to today. Okay? But I have to be honest. I have a few more minutes, Alessandro.
Sure. Yes.
Good.
Yes, at least 10.
Ah, fine, fine. I need very few, actually, because I wanted not to disappoint and spend a few minutes on satellite resonance. But I don't have much. I just have a few new results to show that we started working recently with my student Stella Zirti, the one who produced the secular theory that I showed you before. A little bit on the case of the one-to-one resonance between an artificial satellite and the mean motion of the satellite and the rotational motion of the primary, which I have no idea of how to call it. Can I call it a mean motion resonance or not?
That's what they call it.
Yes, that's what they call it.
Okay, but it's not a resonance between two mean motions. It's a resonance between one mean motion and one. Anyway, let's call it like that. Okay, so let's assume I have a particle which should be moving near the vicinity of the one-to-one resonance. That means that this angle is critical. This is the mean longitude of the satellite, and this is the rotation angle of the prime. What you need to do in order to construct the resonant model is you need to go to Kaula's huge expansion and try to find the terms that contain this combination of angles. Okay? Of course, if you have a very high degree, a very complex gravitational model for the moon, you start looking in a haystack for a needle. So you need to say, let's say that, okay, I don't care about all harmonics. I care about harmonics up to order and degree 2, let's say, or 3. So in the lowest order approximation, if you try to find the terms, you will find out that in the Hamiltonian, you would have the Kepler problem plus the correction here. You will have the J2 harmonic, which is not a function of the angles. Okay? And you would have also combinations that have inside sigma, actually they have 2 sigma, related to the C22 and S22 harmonic coefficients. So if a body doesn't have the sectorial term S22, you can ignore it and you can keep only the C22 term. And that's the main term that comes as the main term of the Hamiltonian for the resonance. Now, if I would stop here, it's a simple 1 degree of freedom problem studied by Delsat et al. For the case of Vesta, for example. I wanted to do a little bit more complicated, so we said, let's see if there is a deformation of degree 3, a J3 term, what would happen? So if I have a J3 term, it does not give me a contribution with 2 sigma, but it gives me, as before, the angle sine G. So therefore, I constructed 2 degrees of freedom problem. And I want to see whether the coupling between these terms would give me something interesting or not. Now, again, not to bore you, a series of small transformation plus an expansion to degree 2 in eccentricity, not inclination, I don't care because h is a constant there. The node is not there in this Hamiltonian. I get something like that, which contains linear and square root terms in G as I expected, and of course you have the C22 and S22 contribution with the resonance. Now, here I can follow exactly the same set of canonical transformation that I followed before for the 3-body problem, meaning I first reduce the secular part. I take only the secular Hamiltonian, okay, I go to Cartesian variables, I find the fixed points, then I translate the reference frame on the fixed point and define the new polar coordinates. So linear, resonant, proper, 3 elements. And I extend the transformation to the resonant part, and I get this. If I also do the same trick, I expand the Keplerian term to degree 2 in sigma capital, which is now the deviation from the exact resonance location. Okay? It is JPC that I had in the previous.
And where did Citric 0 disappear?
Which one?
Citric 0. I don't see it anymore.
It's hidden in these coefficients, don't worry.
Okay.
But basically, yeah. If you do that, you see that the terms combine, and now you form combinations of the resonant angle with the proper frequency of the proper angle of the perihelion, which is this W. Okay, so I could kill the middle line to have a secular problem plus the 1 degree of freedom resonant approximation. This would be my 1 degree of freedom approximation. The 1 degree of freedom approximation would give me pendulum-like dynamics for which I can compute everything, stable point, unstable point, width of the resonance, and so on, for different values of the initial inclination, and I have a complete picture. Okay, these are two different projections of the level curves of the Hamiltonian for different initial inclinations and eccentricities. Actually, here you would see that I have more. Okay, here I have two islands like that. There I have the two islands in a different sense. So the stability between the fixed points changes beyond a certain point in eccentricity, but I wouldn't use that because it's beyond the capabilities of my expansion. Okay. The interesting part is that if I introduce now the second degree of freedom, which clearly has a much slower time scale, actually, I get something like that. These are now Poincare sections of the 2 degrees of freedom problem, and they have a chaotic region around the main island, of course. This is for a value of J3 over J2, which is the one that Tricarico and Sykes computed for Vesta from the simple model. And this is for a value which is 3 times as high, just for fun. So, of course, the size of the chaotic domain increases there because the J3 term is more important. So the coupling between the sigma terms and the W terms is more important.
So the left is for the Earth, and the right is
No,
for Vesta.
for Vesta. This is for Vesta, this is for a more deformed body. That does not exist most likely.
Okay.
Okay? But it's... And because the time scales are so different, the size of the island is big and the size of the chaotic domain is small, according to the scheme we showed before. And I can actually use a little bit the frozen pendulum approximation to find more or less approximately the limits of the chaotic motion. For example, this is now a Poincare section on the other set of variables, square root of gamma times cosine, square root of gamma times sine of the W, projected here for a given energy level and a given initial inclination, and this is the chaotic domain. Okay? So in principle, the frontal pendulum tells you that on my secular dynamics, I superimpose a pendulum, and if I compute the points that should actually belong to the separatrix of the pendulum, then I have a curve in phase space that gives me the locus of the separatrix on this projection. And any invariant curve of the secular dynamics, meaning I take the previous Hamiltonian and I average over sigma, assuming that I am inside the resonant domain, or outside, sorry, outside. Okay? Any invariant curve in the Poincare section of the 1 degree of freedom problem that actually intersects the black curve should become chaotic. This is actually, if you like, similar to what Wisdom had shown for the 3-to-1 dimensional resonance of asteroids. Then Neistat did the computation much more rigorously, finding also what is the jump in the adiabatic invariant when you cross the critical curve and so on and so forth. Anyway, you can do that. It's simple. You can use the equations of the 1 degree of freedom problem to find out when a point on this section would correspond to the separatrix of the pendulum and compute analytically this black thick curve, which, as you see, is slightly off-center. Therefore, all centered concentric circles, some of them would actually cross the black line, either in the lower part or in the upper part of the black curve, because it's slightly off-center. All these curves that intersect the black curve become chaotic. Therefore, the limits of the chaotic domain on this section can be given by these points that you can compute essentially analytically in the frozen pendulum approximation to some accuracy, of course, not very high. The interesting thing is that if you can compute this, you compute essentially a dispersion in mean motion for the satellite that you could use. For example, let's say I don't know anything about the body, I'm trying to see if it has a J3, I compute the dispersion and the frequency of the satellite to see if it's compatible with a given value of J3. Of course, this is not what somebody would do. I'm just making a theoretical experiment here. Okay? But it's useful. In fact, I haven't checked, but it might be that this chaos is even observable, but I don't know on which time scale, because, as you know, there is a case on which it can be observed, which is the Prometheus-Pandora system of satellites in Saturn, because it has a Lyapunov time of 3 years. And you can see the variation in mean longitude of both satellites if you observe long enough. And you can see actually that the mean longitude is never on the value you predict. And hopefully you do it for a few tens of years, you could probably see a dispersion which is more or less random around the predicted value. Anyway, this is obviously not long-term chaotic diffusion because the 2 degrees of freedom problem restricted on an energy manifold, so the chaotic regions are just layers in phase space on which you will remain bounded for all times. If you add a 3rd degree of freedom, things might change. But this was just an example to show the power of using simple Hamiltonian models and simple tools to really do a meaningful analysis of the dynamics, either for the asteroid case or for the satellite case. And with this, I actually made it. I didn't expect so, but that's it. Thank you.
Thank you very much. Special thanks to Kleomenis, who made a special effort to be here due to a very busy period in his life, and he actually made a rush. Like Sunday will leave us this afternoon because it's something else to do.
It's something that I hate to do because I run into the risk of being labeled as the a student of somebody who does it often, but I don't want to do it.
So, thank you again, and questions?
Just a comment that is in your very nice lectures, you didn't mention Nekoroshe's theory, which, by the way, is a very powerful tool, which is related to this kind of normal forms, to provide the stability domain of the asteroids. And in fact, we have examples in decades ago where Nekoroshe's theorem gave already decades ago, and with that power of the machines, results which were consistent with the physical applications, with concrete asteroids.
Yes.
I guess that if some young people would like to go in that direction now with the current computational tools, then it could even be better, and we have the hope that things could be different now.
It's true. Well, I cannot really comment on the general applicability of the Nekoroshe theorem. I know that there was some search by Massimiliano Gucci and people who show different cases where it can apply or not in the asteroid problem. On the other hand, I didn't mention much because, as you know, I'm not an expert on that. I know very little things about really producing rigorous normal forms of high order and using the Nekoroshe theory. And I'm actually, so the lecture was actually focused on the opposite problem of finding the asteroids that diffuse, that would not be stable in the Nekoroshe sense. But of course, a complete, a student who would like to have a complete grasp of the theory should be able to do both.
I'd also like to make a comment which is about, let's say, historical perspective. That is, it was mentioned what we did 20 years ago. At that time, I mean mid-1990s, not the 19th century, nobody believed that there could be really young asteroids. When we say the age of the Veritas family was less than 50 million years, this was a big surprise. Because everybody believed that most of the space, apart from, of course, the Kirkwood gaps, most of the space of the asteroid belt was in a Nekoroshe regime. Now, the fact is that, of course, the Nekoroshe regime applies after removing the Arnold web after the given order. Now, the fact is this Arnold web is very, very important and also because of various reasons, amplification effect like the great inequality and so on, the opportunity of finding resonance are many. So now we are aware that the number of strong chaotic holes, which the diffusion is comparatively large in the asteroid belt, are much more than what it was believed only 20 years ago. So the Nekrasov theorem applies certainly somewhere, and somewhere it doesn't, because there are other mechanisms which dig comparatively fast transport lanes. And this gives an extremely complicated structure. Now I think we have a better understanding of this now. The number of families which are young is quite large. Now we have at least half a dozen families which are known to have ages which are less than 50 million years. And also below 100 million years, there are quite a few. So in other words, I support what you say. The use of Nekrasov method should be attempted, but we have to be very careful in attempting where they work.
Yes, of course.
You have to select the right place. It's a very stable region which can be identified. I can tell you where to look, because it's clear that there are regions which are extremely stable.
But this is obvious. I mean, do Nekrasov theory where you can do it. Otherwise,
The point is that there was a very long idea 2 years ago on where you should be.
I was just wondering, the resonance that we were looking at, if you include, for instance, like the cosine mechanism into this story.
You mean about the satellite or the asteroid?
For instance, the asteroid problem.
Okay.
And I mean, from what I can recollect, it's been a while since I looked at the cosine effect. When you have the large planets on the outside, you have, over long enough time scales, the cosine mechanism as a way of at least inducing an extra layer of complexity within the
Yes, but there are some conditions for the cosine resonance to occur, right?
Right.
So if you are outside the mean motion resonance, you have a restriction, strong restriction on the inclination. You have to have high inclination.
Yeah.
If you are inside the mean motion resonance, the mean motion resonance has to be strong enough to induce the cosine effect. So something that is probably not obvious from what I said is that the frequency of the motion of the perisender is a small positive number everywhere in the belt. And it becomes faster and faster as you approach the perturbing planet. However, the resonance, a big resonance, would actually induce a frequency of the perisender in the opposite sense. So if the resonance is strong enough, you can force the frequency to be much slower, so to reach the frequency of Jupiter, the frequency of Saturn, so the new 5, the new 6 secular resonance, or even have cosine resonance inside the resonance, the mean motion resonance domain. But this has been shown only for the very strong mean motion resonances, not for the, let's call them, I don't like the term, the diffusive resonances.
Okay, thank you again.